when we're looking at this, we could have just given up, but I think an easier way to start this problem would be to do what? Like, what could we do to start this problem? Thoughts? Jade, you got one. How'd you start this problem? You drew a triangle. Okay, what kind of triangle? Yeah, a right triangle. Okay, so mine's not going to be perfect. You're going to have to forgive me on that, but it's okay. Hopefully they can see that. Can you guys see that? Okay. Do I need to make it thicker? Probably. All right. So then what do you know about this triangle then, Jade? Five over 4 seems to be side lengths. So we know that the tangent of x is 5 over 4, and Jade is telling us that those are side lengths. So the question becomes, what side lengths are they? What side lengths? Yeah, Jerry. All right, so the 5 is the opposite of x, the 4 is the adjacent of x, so where the heck is x? Bottom corner? Yeah. So it's kind of the angle, right? Because we put angles into tangent functions or angles into trig functions, so we know that that is an angle. And then we get out the opposite over adjacent ratio. So we know that this is what it looks like, maybe. Why do I say we know that this down here is what it looks like? Maybe. Why did I say maybe? So again, the question is, why did I say maybe? Pop squat. Carter, why did I say maybe? You did sit, right?
Yeah.
Yeah, okay, good. I knew that. I was just making sure you knew that. So why did I say maybe?
Is probably wrong. Could be because we don't know what the actual length of x.
So could I change the look of that triangle and like magically change x? The actual answer is maybe. So, Alicia?
Well, maybe because x could also be the top corner, you know, the angle on top.
So if I made it the top corner instead, if I did that, that's not a good line. That's not either, but you have to going to go with it, okay? We're going to pretend that's a right triangle. If I made x the top corner, how big would this side right here be? 5. And this would be 4. Is that really a different triangle? And I know that mine aren't drawn to scale. Is that really a different triangle than the one in the bottom? No, so not really. So again, why did I say then maybe to the fact that this bottom triangle here, you know, this might be what it looks like? Jerry Lee, what are you thinking? Oh, I didn't even think about that. You're saying like maybe the triangle looked. That was such a good answer, Jerry. You should cup that. So you're saying maybe the triangle grew. What could the side lengths be, Jerry?
That's a great question.
Thank you. I like to ask questions. Cole?
You're saying that maybe that's how the thing looks, and that's because like the height, you know what that is from the side, so maybe that's like actually what the angle is, like on the inside of the circle.
Oh, you're not answering Jerry Lee's question? Oh, we'll come back to you in a second. Jerry Lee, what could the size of that triangle, or actually, Trevor, go ahead.
The opposite might be 10 and the adjacent might be 8.
So Jerry Lee said maybe it's a bigger triangle. Would the tangent ratio still be 5 over 4? Sure. Which one would you prefer to use as we problem solve? Red or green? Why? Smaller numbers. I'd rather keep the smaller numbers. It's already simplified, right? But Jerry Lee's absolutely right. We don't know what the size of the triangle was. We just know that it has that ratio. That's a great question. So, when I'm saying maybe, I'm really wanting us to focus on this. In which quadrants could that really lie? Does it have to be orientated in this way? Where could it be? And then for this, I'm going to go to make a circle, like there's our circle. Which quadrants might this triangle be in? Mitchell?
Maybe the first or third.
Could be in the first quadrant. Or you're saying in the third quadrant. So we could have, we could have 5 and 4, or we could have, 5 and 4, because x is going to be that center angle right in there. Why does this matter? Because now we're not just thinking about what does the triangle look like, but also how is it orientated. Why does that matter? Trevor?
The green triangle, both the legs would be negative.
On the green triangle, we'd have to think about like positive versus negative side lengths, right? Like those are negative legs. They're directed legs. They're going backwards and down. As opposed to the blue legs, we have to think about being positive. Okay, so we know at this point in time that the triangle indeed looks like this, but it could be orientated like either one of those. So we at least understand the problem, and we've already solved the first question. In which quadrants could it lie? 1 or 3, which is great. So how are we going to find the possible values of theta? Or, maybe instead of being like the possible values, how could we find a possible value of theta? Turn and talk because you guys have been kind of quiet for a second. Start the recording in. How are we going to figure out what the angle could be? Tate?
What we did was we knew that we had to use the inverse function of the function. And so we plugged into our calculator. We did the second tangent, which gives the tan to the -1. And then we plugged in the guide over 4.
Yeah, and I'm going to run out of space real fast. So the question becomes this tangent -1 function, and I just want to reiterate this because this is going to become super important for us. You said it's approximately 51.3 degrees. Is that what you said? What is this new tangent -1 function? Like you said inverse. That's awesome. What does that mean for us? Like, how did we go from here, right, to there? Like, what does that mean? What's the difference between tangent and inverse tangent? What's the difference between tangent and inverse tangent? Tim?
On the original tangent function, you're given side lengths from which you already have your angles for.
Wait, hold on. The original tangent one, we're given our side lengths?
Okay, now, what I meant to say was, on the original function, the tangent of whatever x variable is 5/4. Well, on the inverse function, what you're doing is you're taking the result and reverse engineering it to find the angle which you would originally have in the first one.
Okay, so you're saying reverse engineering. So you're saying in the tangent one, we would have maybe taken something like this, and it would have given us something. And you're saying inverse tangent will actually just take and reverse engineer what we had already had. I get that idea. I don't get that idea. So in the original tangent function, what is it that we really start with? What is that thing that we're starting with? Describe it, Gabe.
I was just going to say it's the angle that you're looking to find a side length.
And then we get a side length ratio, right? Yeah. So tangent will take an angle and give us a ratio. So inverse tangent will take a ratio and give us a angle. So it's really asking the opposite question, hence inverse function. It's doing the opposite thing. All right, so we got 51.3 degrees. And that is using inverse tangent. So how does this help us? How does that help us? What does that tell us that our possible values of theta are? How many did you? Now this answer of like, I have two angles that do that makes sense. So what angles did you get then? You got theta could be what? Trevor?
51.3 and 231.3.
How did you get 231.3?
Added 180.
Why?
Because, and again, if it's in the first quadrant and I need it to be in the third quadrant, it's 180 degrees around the other way. So it's like half the circle.
I see that, I don't see that. So instead of just having this angle here, you see it, we could actually say, all right, we have 180 degrees, and then we have that angle. Because that's what we found, right? Now, so we have two angles. In theory, are there other angles that would work? How many? Show me with hands. Hands, man, I said hands, not arms. I don't get this whole, like, eagle spread arm thing. Like, what is this? You're flying?
Infinite.
Infinite. Why infinite?
Because you can continue adding 180 or subtracting 180 and getting coterminal angles.
Ooh. Alicia?
I was just wondering, so you know.
Hold on. We got to continue with Trevor's thing before we answer another question. He said, because we could keep adding 180 to get coterminal angles. I agree with that. I disagree with that. Schaffner, what do you think? So you're saying, like, take that blue one and add 360, or add 360 again, or add 360 again. So really, there's an infinite number of angles that would make this happen. Now, Trevor, you probably just saw there's a 180 degree difference between the green and the blue. The green and the blue, in theory, aren't coterminal to each other. But you're like, hey, we can get to either one of those spots by adding 180. And that's cool. All right. Alicia, you had a question.
Yeah, so you know how at the beginning you said that the triangle could be oriented in another way where theta is at the top corner. So that...
We have possible values of theta. So then in part B, I said, all right, so suppose x is then actually in the third quadrant. What are the values of the other trig functions? And so I'm going to go ahead and get rid of everything that's not third quadrant for us. And then, you guys can give me those functions. So be ready to go because I'm going to call in whoever I want. All right. So let's get those values. Give me one. I don't care what it is. Jade. Jade. Come on, you can give me one. As she's thinking, like, I found it funny that I used theta here when I was actually talking about x up there. Did anybody else notice that? Who the heck is this guy? Seriously, like, use x, painter, like, or use theta, painter, but be consistent. That's just stupid, Sorry I did that. Okay? Come on, Jade. Give me something. Any one of the trig functions. You could give me secant of x. You could give me cosecant of x. You could give me cotangent of x. You could give me sine of x. You could give me cosine of x. I'm trying to filibuster time for you. Did you notice that? All right, good. Did you get one yet? If you were going to advise Jade, yeah, it'd just be 4 over 5. So, and I saw you with your hands. You're like, isn't that just the reciprocal? Like, I don't really need to think for that one. I can just flip it. Bingo. There's cotangent. What about the others? Pick one and give it to us. Cole?
Science, 5 over 9.
5 over what?
9.
How'd you get 9?
That's better than 0.
So you got sine as being 5 over 9 and use the Pythagorean theorem. Did it actually come out to be 9? I'm pretty sure it doesn't. So could you explain to me how you use the Pythagorean theorem? Because I heard you say Pythagorean theorem.
So you take one of the lengths squared plus the other length squared equals the hypotenuse squared. I guess the base squared.
Okay, so we get 25 plus 16 equals h squared. Did you just square root everything right there? Is that how you got 9? You just said 5 plus 4?
I mean, I'm not sure.
Oh, okay. And we'll have that conversation. You can't do that because if you think about the order of operations, I have to add those numbers together because I'm square rooting it all together. I'm not square rooting the separate pieces. So we're really going to get, what, the square root of 41 here? And we'll talk about reducing later. I don't think that's reducible anyway, so we're good. So then what would actually be the sign of x? Cole?
5 over square root of 41. Hold on. I gotta find the square root of 41.
Give me another. Don't fix somebody else's. Gabe, give me one.
So for cosine,
Yeah.
I have 4 square root of 41 over 41.
Give me another. Mitchell.
For secant negative square root of 41 is 1.
Oh, I'm loving this. You guys are awesome. And then cosecant. Cosecant. What do we have for cosecant? Trevor.
Negative square root of 41 over 5.
There are obviously debates that were just started. So, things that I'm noticing. 1, my screen is pretty cluttered, so I'll get rid of some of that stuff. 2, there seems to be a debate about what? Sine. What do you mean? Is sine positive or negative? That becomes, ooh, you can't really see the purple for you guys, can you? All right, purple's bad choice. So is sine positive or negative? That's a great question. What other debates are raging? Should there be any negatives in the first place? So negatives, question mark, question mark. I'm also seeing, like, I know that there's this link, right? Like cosine is really adjacent over hypotenuse and sine is really opposite over hypotenuse. But look, like, look at these two. I'm not seeing the same, like, you know, they're supposed to be over hypotenuse, right? I'm not seeing the same over hypotenuse. What the heck is going on there? So we're having these debates about negatives and we're having these debates about hypotenuse. Turn and talk. So somebody solve one of these debates for us. Is sine, you know, are those positives versus negative? What the heck's going on with the hypotenuse? I don't really care. Pick one. Chloe, go. Well, could you explain to me where these negatives are?
So the 4 is negative on the x-axis.
Because it's going backwards?
Yeah.
Got it.
And same with 5.
So you're saying the 5 is negative 2. What about the square root of 41, which we found for the hypotenuse? That's just a radius. Think about, like, why the x value is negative, right? We have a negative x value there, right? We're going backwards. Think about our y value. That's actually going down, right? And we know that y value is, like, we're looking at those coordinates. But that radius, like, where would a positive radius be or a negative, you know what I mean? That's always just the length from 0, period. So this is actually never negative. That radius you could always consider to be positive. It doesn't have a direction. It has 360 degrees worth of direction. So how the heck would we have a positive and negative direction? You know what I mean? It's kind of weird to think about. So does that change any of your thinking there, Schaffner?
Yeah.
So what are you thinking then?
Only it's going to positive and negative in each trig functions.
So which trig functions?
So like in secant, it would be negative because the 4 is negative, the square root was positive.
Got it. So you're like, hey, that 4 was negative. So then similarly, like cosecant, you're saying would be negative.
Yeah.
And then similar, like cosine and sine.
Yeah.
And Jade was over here, like, she's like, well, those are just the flipped ones, so those would have to be negative, like, if, that matches. And that was the argument in the first place. What about tangent and cotangent? Are those negative? Why not, Gabe?
Because your cotangent and tangent is like your -4 and -5, and those two negatives cancel out.
Got it. So it's like, don't even put them, Painter. Awesome. So we've solved the negative debate. So the question becomes, can we solve this whole hypotenuse debate? This debate right down there. Like, is it a hypotenuse? What the heck happened? Jerry Lee? So you're saying, like, they're both correct. It's just not in a pretty form, a rationalized form. So how would you rationalize that sine value? And what is rationalizing really doing? Getting rid of the square root in the denominator. So that's where we're getting this, right? Because ultimately, if you look right here, we're really doing the square root of 41 times itself, which is really the square root of 41 squared. And how do square roots and squares compare to one another? They're what? They are inverse operations, right? They're going to do the opposite thing. So if you use both, guess what happened? Absolutely nothing, right? It's like giving somebody $5 and then taking it back away. Like, you didn't do anything except for make them cry. So, right? And that's what it would do if we actually did the math for it. Find the square root and then square it back. Like, you just make yourself cry. You'd be a masochist, right? And so that's where we're getting, this prettified version of cosine. Wow, that's sloppy. My screen's not pretty. And then sine has that pretty version right up here. What questions might we have?